Welcome to today's webinar on accelerating simulations with MSC Software and NVIDIA solutions. Today's speakers are Dr. Travis Austin from MSC Software and Bhaskar Rajagopalan from NVIDIA. Travis is a senior HPC manager at MSC Software, leading a team of developers working to accelerate MSC Nastran on high-performance computing architectures. He has over 15 years of experience working on a wide variety of applications ranging from plasma physics to electromagnetics to structural mechanics on HPC systems, ranging from a few processors on workstations to thousands of processors on large government supercomputers. Travis has a PhD in applied mathematics from the University of Colorado. Bhaskar currently works at NVIDIA, managing strategic alliances with the independent software vendors in the computer-aided engineering and electronic design and automation market. For over 20 years, he has helped manufacturers with the technical transformation to create innovative products using design and simulation solutions. He has a master's degree in mechanical engineering from the University of Toledo. Here is an outline of the topics we will cover for the next 40 minutes. Starting with specific challenges and trends we have observed based on surveys as well as talking to engineers and IT in the field. And then we will review NVIDIA solutions and GPU computing relevant to MSC Software. You will also see techniques or methods and options to run MSC Nastran using GPUs, and then look at some benchmarks that we have conducted to understand the performance benefit of NVIDIA GPUs. Now I will turn it over to Bhaskar, who will talk about challenges and trends seen by product manufacturers, engineering and IT departments, and explain how NVIDIA solutions can help.
So it is obvious that products are becoming increasingly complex today, and manufacturers have to create innovative, higher quality products and get to market faster. Now for engineers, what does it really mean? These challenges translate to better understanding of form, fit, and function of complex products before actually making physical prototypes. Now how do they accomplish that? By building high-fidelity simulation models on several design variants and use of appropriate hardware and software for accurate simulation. Now, NVIDIA has been talking to engineering and IT departments to understand what is really bothering them. From an engineering team's perspective, as you can see on the slide, it boils down to reduction of overall simulation time, which helps in increasing simulation throughput. Now, of course, some are looking for solutions that can help them complete the simulation within a stipulated time. Let's say, within the hour or perhaps within a work day. Thus, they can make decisions before a meeting ends or before the workday ends. And some are actually looking to access data remotely in a secure form. When I say data, we are talking about simulation data, computing, simulation computational data, storing simulation data, and so on, while they are outside the office. So while they are on the road, beyond their office desk. While they do that, they want no compromise on graphics performance. Now it seems like they've all tried different methods, but not every method is optimal, convenient, or desirable. Now their IT departments, on the other hand, they recognize the needs and demands of engineering teams, but they grapple with several issues. First, they need to centralize compute and storage assets for better hardware and software utilization. Second, they need to deploy technology quicker so that globally distributed teams can easily come on board while keeping costs down, which is actually the third challenge. The fourth challenge, protecting intellectual property, is one of the key requirements that needs to be met. So here are some very interesting data points specific to MSC users based on a survey that was done by MSC Software about a year ago. The survey focused on a broad range of topics, but here we are including only a few aspects where NVIDIA solutions can address these specific challenges. These include the product development process, performing simulation earlier in the design cycle, and supply chain collaboration. So if you carefully look at the first three aspects, these are about delegating or outsourcing simulation tasks beyond the core simulation team. When we say bringing simulation earlier in the design cycle and allowing engineers and suppliers to perform simulation, we mean that the teams are distributed and not in a single physical location. Thus, we see a strong need for remote and centralized simulation data access for efficiency and productivity. Now, the last two aspects that you see here, they point to the fact that more computations are needed that need to be performed in a short period of time. So the trends and challenges that we actually see here indicate that there is a big opportunity for you, the customer, MSC, and NVIDIA to shrink the product engineering cycle, starting from geometry all the way to post-processing of simulation results. Let's now see how NVIDIA can help address the visualization, computing, and virtualization needs. Now, for those of you who may not be familiar with what a GPU means, GPU stands for Graphics Processing Unit. We will talk about how GPU computing works in a couple of minutes. Now, the NVIDIA solutions for MSC software include Quadro GPUs for professional design and visualization, Tesla GPUs for high-performance computing, and NVIDIA GRID technology for virtualized desktops. Now, NVIDIA GRID is the technology that delivers rich graphics anytime, anywhere on any device. Now, besides these, NVIDIA has GeForce GPUs, for example, for gaming and other visual computing solutions that are beyond the scope of today's presentation. Now, I should say that some manufacturers have already begun to address some of the challenges that we just reviewed a minute ago by including these GPU solutions. And many of them are already using NVIDIA Quadro GPUs for workstation graphics, as it's been around the market for quite some time. Now, some have started adding Tesla GPUs to existing workstations, servers, and clusters, simply to speed up simulations instead of simply scaling out or scaling up their servers with just CPU technology. Now, switching from physical desktop to virtualized desktops is also increasingly common. So what do I mean by virtualized desktops? So when you talk to people, when people talk about virtual desktop infrastructure, shortly known as VDI, or perhaps they refer to HVD, hosted virtual desktops, they're basically talking about working with virtual machines rather than physical workstations or computers. In such environments, NVIDIA GRID allows to virtualize GPUs, and thus simulation, pre-processing, and post-processing can be done remotely with uncompromising graphics performance. Now, before we go further, for those who are new to GPU, let's review how GPU computing works. On the left, you see CPU on the blue color, and on the right, you see GPU on green color. So obviously with CPU, the blue squares represent the cores, CPU cores, and for GPU, you see hundreds of those green squares. Those are the cores. So you're looking at thousands of cores in GPUs versus few cores in CPUs. Now, graphics is a highly parallel job, and GPUs are therefore great throughput processors using thousands of cores. CPUs, on the other hand, are latency-optimized processors, and much of its design has been dedicated to make a single program go fast. While NVIDIA GPUs have historically been known for graphics, in the past several years, GPUs have evolved from just doing graphics to becoming more general-purpose processors that can do scientific and technical computing. So for this reason, sometimes they are also known as GPGPU, which stands for General Purpose Graphics Processing Unit. So GPU computing is essentially the use of CPU and GPU together. These GPUs can't operate without a CPU, so they are sometimes called as co-processors. Now, since we just talked about GPU for computations, I would like to address one common question that has been asked way too often. I just a minute ago talked about the different solutions, namely Quadro, Tesla, and NVIDIA GRID. So specifically focusing on Tesla, which is kind of the crux of this today's presentation. Now, the common question is, why should I use Tesla and not Quadro or GE Force? And the answer is a long answer, but I wanted to ensure that everybody understands what Tesla GPUs really provide that GE Force and Quadro doesn't provide. First, Tesla is much more than just a GPU board. It is a computing platform that combines GPUs and a whole comprehensive ecosystem of software developers, software vendors, data center system OEMs that give you unrivaled performance. Now, specifically for end users such as you, NVIDIA's Tesla has features that are simply not available in GE Force hardware. Now, these features have been classified here on the slide as performance, HPC solutions, and data reliability. If we take a look at performance, this is the most important aspect, if at all, any of the other aspects add value to the end user. When you look at performance, many scientific codes compute in double precision today, and MSC Nastran is no exception. Tesla GPUs feature high performance, high double precision floating point performance. GE Force cards, on the other hand, have high floating point performance in single precision mode. So they simply will not do the job that Tesla boards can do the job. Now, they also have larger memory that helps applications such as acoustics, electromagnetics, and CFD calculations. Now, you might be using other products beyond MSC Nastran, so certainly Teslas are the way to go. Now, also there's a Tesla Compute Cluster Driver, shortly known as TCC driver. They take care of kernel launch overload, and also they allow use of Windows Remote Desktop. Now, when you look at HPC solutions, Tesla GPUs have much longer life cycle, typically about 2 years availability, which is useful for enterprise customers who have a need to replace or add hardware after initial deployment. Now, that's not the case with GE Force, typically because of the fact that it addresses the gaming market. They change constantly, and you don't really have a long shelf life. Now, the next aspect is form factor. So Tesla is supported in certified servers, blades, and workstations. Tesla also provides you with cluster and GPU management software, wherein you can do diagnostics such as monitoring temperature, usage, and power. Excuse me. So the third aspect is reliability. Now, simulation computations, they need to be error-free. So Tesla GPUs come with ECC memory protection. GE Force, on the other hand, does not have ECC protection. As a small error in graphics, they usually go unnoticed. So when it comes to simulation, obviously your accuracy is paramount, so there is no compromise in terms of getting errors in your answers. Now, the next aspect is we call it zero error stress tested. This means that the hardware is stress tested for many days with zero tolerance for error. Now, ISV certifications, independent software vendors, they certify their apps only on Tesla. And also, it is a good point to note that Tesla boards are manufactured by NVIDIA to guarantee highest reliability. And also, you have NVIDIA support for bugs and feature requests. Now, most of these are also available in the Quadro line of products, but the lack of double precision makes Quadro useful just for graphics. So I hope you have an idea of the value of Tesla GPUs. And also with advanced system management features, accelerated communication technology, and supported by popular infrastructure management software, Tesla platform provides computing professionals the tools to easily build, test, and deploy accelerated apps in the data center. Now, we just focused on Tesla. So the other solutions include Quadro and GRID. So to better understand how these solutions fit into the typical simulation workflow, I've put up a few slides explaining that aspect. First scenario is a workstation with a Tesla GPU for computation. So you have a workstation, and you might optionally have a Quadro GPU for graphics. Now in this scenario, all the data resides locally in the workstation. Now let's see a scenario where a cluster is used instead for computations, serving multiple workstation or PC users. Now for better understanding, I'm mapping the simulation workflow with a flow chart. So here you see the pre-processing, solving, and post-processing. So when you have the workstation with optionally a Quadro, sometimes people just use integrated graphics or perhaps even GeForce. So you start building the model shown by the little red dot on the screen with your workstation and your software. You then transfer to your cluster. So here the difference is that in addition to the workstation, you actually have a cluster where there is a Tesla GPU, and that's where you do compute. So you need to transfer data from your local workstation to the cluster and then do computation using the GPU and CPU. And in the process, you're generating humongous data. This then needs to be downloaded back to the workstation, or sometimes it ends up going to another user because there are separate departments that actually look at the results and then make design decisions as to what they could change. And then the whole process continues all over again. So here you see that there is a Tesla in your cluster as well as a GPU locally on your workstation. Now there is another workflow where if you see, this is going back to the previous slide. So the previous slide, we just have HPC cluster. Now I have something in addition, grid. So what we're doing here is, notice that on the workstation where you have a Quadro GPU, I'm actually removing the Quadro GPU, and instead we put a grid card on the cluster. Now the advantage here is now we are making the NVIDIA GRID GPU available to a broad set of users and not just a single user that is attached to a physical workstation that nobody could access. Now because of the fact that we now move the GPU to the cluster, we no longer need a heavy-duty workstation. Instead, that can be swapped with a simple laptop or a tablet and still be able to access all of the things that the user wants without making any compromise on graphical performance. So here, the same process continues. Follow the red dot. You prep your model locally on your workstation or your laptop. You move the data to your cluster. You do your simulation run, which generates a lot of data, but then the beauty is you're not moving the data again locally to your desktop. You are using a thin client to do the post-processing using NVIDIA GRID technology. So what happens in this process, you're simply streaming graphics through your local area network or a wide area network. Now, this method also provides you ultimate data security. Even if your laptop is stolen or broken, you don't lose the data because all you're looking at is just your streamed pixels, your graphics. Then the whole process follows all over again. Now there is another workflow where we've basically taken both pre-processing and post-processing to be done on a thin client. So notice that you have a workstation with a Quadro, but then for this workflow, you don't need them. I'm going to take off my Quadro GPU, and I'm going to add this grid card to the cluster, and then swap my heavy-duty workstation with just a simple laptop. So it's as easy as that. Then again, you start prepping your model. Now in this case, even though you're locally accessing through a thin client, your actual data sits on the cluster. So you have ultimate security to access data. And this works pretty well, especially if you're working with remote users, with working with suppliers where you may not necessarily want to share all the confidential data. So everything's done through this thin client. Now this is how your Quadro, GRID, and Tesla GPU technology can actually help you in cutting down the overall time. So it's not just your Tesla cards that can speed up computation. Great. Now I'll pass it on to Travis, who'll talk about GPU computing at MSC Software.
Thank you, Bhaskar. So in this next section, I want to discuss the capabilities that exist today in MSC Nastran and Marc with regards to GPU computing, as well as future capabilities that are planned for Actran, the MSC Software acoustic solver developed by our subsidiary company, Free Field Technologies, or FFT as we call them. The majority of the GPU acceleration that has already been performed for most structural analysis tools like MSC Nastran and Marc is with respect to the factorization of the matrix within these simulation. In any structural analysis simulation, the core component is the matrix A that represents the stiffness in the discretized model. To obtain the displacements in response to applied forces, we must factorize the matrix into one of several forms. Here we see a factorization of the matrix into its Cholesky form. And to generate the Cholesky form, large, dense matrix calculations, typically you hear the term degems, are required to turn the matrix A into LDL transpose. And it's this work, this large, dense matrix calculations, or the degems, that can be efficiently performed on the GPU. In MSC Nastran 2012.1, the work was finished at the second half of 2011. MSC Software delivered the first accelerated solver on the GPU using this previously described procedure for real and symmetric matrices. This, of course, allowed for acceleration of several solution sequences, like solution 101, 103, and 400, where the matrices are typically real and symmetric. Complex and unsymmetric support was added in the MSC Nastran 2012.2 release. And of course, that broadened the set of solution sequences that we could cover, including now solution 108, 109, 111, and 112. In the 2013 releases, 2013.0 and 2013.1, we improved the performance, vastly reduced use of pinned host memory, and the ability to handle arbitrarily large fronts on a single GPU with the 6 gigabyte device memory. Marc relies on a different matrix factorization method than MSC Nastran. Nastran has its own native factorization method. Marc uses the BCS Lib GPU solver developed by Boeing and Access Analytics. The GPU solver was based on the original BCS Lib EXT solver, and the Marc development team worked closely with the BCS Lib GPU team over the years to release Marc in 2011 with GPU support. In the BCS Lib GPU solver, the parallelization includes the update step and the panel factorization step, including the triangular portion. The Marc team was instrumental in improving the performance and finding several bugs that eventually ended up delivering a very robust solver. Note that this also has out-of-core support and provides enhanced performance to the domain decomposition iterative solver in Marc. As with MSC Nastran, the GPU solver in Marc is best for solid element models and can deliver up to 3x performance improvement. Now we're going to change slightly when we talk about Actran. Actran is our acoustic solver developed by our subsidiary company FFT. Note that the acoustic technology in Actran is also used in Nastran for both interior and exterior acoustics. One of the technologies available in Actran is a time domain solver that relies on the discontinuous Clerk method. As an explicit time domain method, it is a prime candidate for acceleration on the GPU. Currently, the DGM method accelerated by GPUs is under development, but has already shown a greater than 10x speedup when using a Tesla K40 GPU. This new feature in Actran is expected to be in Actran 16 to be released at the end of the year. This is one case where we're not relying on a matrix factorization method as we are with Marc and Nastran, but we're still getting the great performance using the GPU. So I've discussed MSC Nastran, Marc, and Actran in generality. Now I want to focus on the specifics of GPU acceleration in MSC Nastran with a focus on usage and newer performance results. First, however, it is useful as a user to determine if you have a GPU on your Linux system. Here I'm focusing on Linux, but of course there's ways to find out on a Windows system if you have a GPU. One command that you can use to determine if you have a GPU is the NVIDIA SMI command. This is known as the NVIDIA Systems Management Interface command. It will tell you additional information about the GPUs, as you see on this current slide. Here we can see that this is a system at MSC Software with 2 K40 GPUs, and neither of them have any processes running. If you issue this command on the command line while you're currently using a GPU, you'll see the processes associated with those GPUs. We're trying to do a much better job in future releases of Nastran to provide help to the user. In our 2016 release, that is going to be released at the end of the year, we're going to provide additional output at the end of an FO6 file to tell you if you have a GPU and also where you should use it. It will also provide you a reference to the command that I just described. It is, as I said, it is very useful to run a job with a GPU and then in another window run this command and check to see that the processes are actually using the GPU. So I mentioned before that solution sequence is supported with the GPU. It can be used in all of the following. One thing to note is that for solution 103, it is only useful for the Lanczos method at the current moment. We do have plans in the future to address ACMS, since we have a big redesign of the ACMS algorithm that's expected to be released in the future, but for now it's only supporting Lanczos. So in the next several slides, what we're going to look at is when the GPU performs well, how well does it perform, and when is it recommended to be used. So now we're going to look at some actual performance results. So how do you use the GPU with Nastran? The first thing that you have to do is you have to issue the GPU ID command option on the command line. You can see it here in gold. And after you've run the job, this is, for example, a Solution 101 job, you want to look at the FO6 file, and if you do a search for the FO6 file, you'll see a statement that says that the MSC LDL sparse factorization was run on the GPU device 0. So this is another way besides the NVIDIA-SMI command to see if the GPU was being used in the simulation. Okay, so now we know how to actually use the GPU. Now let's talk a little bit about how to get the best performance. Just running the GPU as of our current releases without using any system cells will not always deliver the best performance. Currently, system cells controlling the factorization on the GPU are necessary for Sol 103, 101, 103, and 400 to get good performance. 4 system cells are currently required for MSC Nastran 2014.0, or one of our recent releases, and these will become the default in MSC Nastran 2016.0. The first system cell, 205, controls the size of the rank in the matrix factorization, and this encourages more large, dense calculations to be performed on the GPU. In this case, we also turn off pivoting, which is okay for Solution 101, but can be troublesome for Solution 400 with indefinite matrices, so you have to be very careful about turning off pivoting. System cells 655 and 656 are added here, but the values used are actually the default, as can be found in our quick reference guide. Again, I just want to note that in the past, we haven't always made the best performance available easily to the customer, and instead system cells have to be used, and we're going to switch this with 2016.0 and change the defaults. For Solution 108, the system is complex, and so there are a few additional system cells required. Here we again are basically setting the rank size that says what are the large calculations going to be used on the GPU. This encourages more dense work on the GPU. Here we turn on system cells 219 and 221. We change the rank size to 320. We've used both the symmetric and the unsymmetric system cells here because for 108, it could be a symmetric or an unsymmetric problem. We want to make sure to cover both cases. And again, for 2016.0, these will become defaults. One last slide before getting to results. One more slide before getting to results after this as well, is running it with an SMP or DMP. SMP is very straightforward. No changes have to be made. Basically, I've been using SMP equals 8 in a previous slide, so you can see how it's used here. For DMP, it requires a little bit of extra understanding. When you say GPU ID equals 0, that's specifying that one GPU will be used With DMP equals 2, there are two processes, and if you actually to the top in Linux, you would see two analysis being performed, and each of these processes would be using the GPU. If you have GPU ID equals 0:1, that says that one process will be using the first GPU and the other process will be using the second GPU. And it's your choice. If you only have a single GPU, you can still run with DMP equals 2, have both processes using the same GPU. An interesting feature of the GPU is the token usage. There are various ways that you can use Nastran licensing. One of them is the token system. In the token system, a single Nastran job requires 250 tokens, and SMP, DMP, and GPU require a different set of tokens, as you can see in this slide. So here, for example, a single Solution 101 job, which is running serial but with a GPU, uses 300 tokens. We will return to this at a later point when we examine the, quote, cost of running with various acceleration methods like the SMP, DMP, and a GPU. So the first model that we consider is a large radiator model with nearly 1.3 million degrees of freedom. It consists of over 300,000 grid points, and it's almost 100% solid elements. We ran this job in the system described at the bottom using various combinations of DMP, SMP, and GPU, and the system cells described previously were used in all these simulations. The first takeaway from this slide is the 2.3x performance improvement from just adding a GPU to the simulation. You can see this in the first two bar, the serial and the GPU. You can see that it's actually a much better option than adding just DMP equals 2. Furthermore, the best performance can be obtained with DMP equals 2 and a GPU for each MPI process. So this might not be obvious to users who typically use SMP, but here's a case where the GPU is a very good option. The second model is an artificial model, but it is an example of a 100% shell element model. We want to show that even with shell elements, you can get performance out of a GPU. This model has over 7 billion degrees of freedom, and it was solved on both the GPU and with SMP. You can see here we get an 8x performance improvement for the GPU. The story is similar for Solution 103. Again, a single GPU can deliver a 3x performance improvement, and DMP equals 2 with a GPU can deliver a 5x. And so if you start thinking about tokens, and we'll get to this later, the DMP and just the GPU can be a very good option. Here's a case that's complex. It's Solution 108. But again, the story remains the same. It's very useful to consider just a single GPU, and the GPU can be a very good option instead of the SMP cores. So if you just use serial plus a GPU, you free up all these other cores on your processor to do other work. I'm going to skip this one since we're running a little bit short on time and go right to the token count study. Now we view the performance in a slightly different way. This is again a solid element model with over 7 million degrees of freedom, and it's a Solution 101. Here what we're doing is taking the simulation time in hours multiplied by the number of tokens required for the simulation. So a Nastran simulation takes 250 tokens, DMP takes 250 tokens, SMP is 200, and the GPU is 50. So in terms of token hours, running in serial mode with a single GPU takes 38% fewer token hours. What that means is if you run in serial with a GPU, you're going to free up those tokens for other simulations much more quickly. Skip this slide too and go to some Nastran tips. So the GPUs, as you've seen, can help significantly in the decomposition of matrix for Solution 101, 103, 108, and really all the solution sequences. But there has to be enough work to do on the GPU. That means it has to be a large enough model, and generally it has to be a dense model. Solid elements are really the best, but you can see that we do get performance out of shell elements as well. Generally, it's not helpful for smaller models to use the GPU just because there's not enough work, and multiple GPUs can be beneficial. Before turning over to Bhaskar, I just want to briefly talk about the future roadmap. We are looking at using the CAE Solver that's going to be officially released from NVIDIA in the future. The CAE Solver provides LayPack, new LayPack options to be performed on the GPU. And this can provide some additional performance improvements when we have dense calculations within MSC Nastran. And we are also redesigning our ACMS solver, and in the future, this redesign is going to allow us to more easily move work to the GPU. So now I'm going to move it to pass it to Bhaskar. We'll talk some more about how GPUs are relevant to MSC software usage.
Great, thank you, Travis. So that was certainly a good insight into Nastran computational performance. Now, GPUs help speed up computation significantly while saving costs by saving token hours, as Travis just mentioned, and that's not all. So the NVIDIA Performance Lab conducted a study on energy consumption when performing MSC Nastran simulations with and without GPU. We took a standard Nastran HPC benchmark problem and studied the performance. Now notice on this chart on the left-hand side, you see a blue squiggly curve and a green curve. You notice that the GPU actually draws more instantaneous power, but the beauty is that the simulation is completed much faster. So overall, the power consumption with GPUs is much less than CPUs. And in this particular case, we are able to get about 2x speed up for the entire simulation while reducing the energy consumption by 47%. Now we talk about lots of GPUs, and many people ask, well, I don't know what GPU I need. So here is just a table. I'm not going to dwell into the details, but you kind of get an idea of what GPUs could be useful for your CAE workflow, whether it's graphics, computing, remote visualization, or virtualization. Now also a good thing to note is that, all these NVIDIA GPUs, they are certified by MSC Software. They do the relevant testing based on specific scenarios, and the updates are provided to us, which we maintain in the listed URLs below. And we do have some updates which is supposed to go in anytime now or in the next couple of days. You'll also see more options to find out, the different GPUs, where to buy, and so on. So just to recap, we did review a lot of things. We talked about, the different challenges, how the challenges can be met by GPU solutions, what sort of MSC software apps are actually GPU accelerated, how to actually run Nastran commands to make use of the GPUs, and then we learned the value of saving token hours, the energy that's consumed, and also some details on certification. So with that, I'd like to have a final remark on what we just reviewed. So NVIDIA GPU solutions provide a superior ROI by accelerating MSC software simulations with fewer token hours while reducing energy consumption. Now, GPU acceleration standpoint, the latest release is MSC Nastran 2014, and it does support various analysis types, from static stress to frequency response to design sensitivity and optimization. Now, Travis also mentioned about the roadmap that MSC has. It has much promise to provide more GPU support in the future, both on Nastran as well as on Actran side. And overall, both MSC and NVIDIA are closely working together to ensure customer success. Now with that, before closing, I'd like to acknowledge a few people in the MSC Nastran HPC team, Marc and Actran team, for their software development efforts. Our special thanks goes to Joe Griffin at MSC and Steve Rennick and Vijay Selapan of NVIDIA for helping with the benchmark runs for this presentation. And finally, MSC would like to thank HP, who provided 2 new server nodes with 2 NVIDIA K40s to MSC Software for development and testing. With that, we are ready to take any questions from the audience.